8 cubes, 3 teams, and 1 winner. Speed cubing is only a matter of milliseconds, so let's see who will overcome the worst. Ever since I was a child, I've had this fascination with Rubik's Cubes. I remember one time my uncle brought me to the store and I had an option. Choose a big robotic spider or a stupid Rubik's Cube brand cube. And that's where my Rubik's Cube obsession kind of began. It wasn't until I actually got into physics that I had this question. Out of all my cubes, which one is actually the best cube? I know exactly what you're thinking. As a full-time college student, it's entirely appropriate and even necessary that I should have to create an ambitious project for my physics class and do countless of calculations which are not only a major waste of my time and energy, but may prove to never be useful a single day of my life. I'm hosting a tournament. The contestants are Jasper, Myla, Kat, and Levi. To simplify the ranking criteria, I have put together this simple chart. First, we have the teams, which I've separated into 3 categories. Team 2x2, Team Normal, Team Shapeshifter, and finally, our control team. These will be cubes like Rubik's brand and slow ones without any magnets, which I will use to figure out all the calculations later on. What team do you think will win, and why do you hypothesize that?
I think that 3x3s will win because in general they're just a more popular cube. 2x2s, they're not that popular because they're not hard to solve. 3x3s are harder, but 4x4s are too hard.
Hello?
Hello. I say team 2x2.
Why do you say that?
Smaller and easier.
Yeah.
I think the shapeshifter will win because, even though the other ones are probably easier to solve, they're just better because I say so.
I think the 3x3 team will win because it's the most iconic shape and type of cube. So I believe companies would probably put the most effort into that one being the most efficient for speedrunners.
Now that we have the teams in order, this brings me to the next step, collecting data. After doing some research, I found there's probably a virus software that can nearly exactly measure the angular velocity, or in other words, the speed of a rotating object. There's just one small problem. My hands don't really move at a consistent enough speed for this to work. You see, any small change in speed or interruption causes major spikes such as this to occur, which put a close to my idea entirely. That was until, drumroll please, the Servo Scrambler 5000! But with all the torque it's legally allowed to give. Since this program is able to calculate these values automatically, I needed a way to understand exactly what is going on when it does that. For this reason, I decided to hand calculate and predict the final speed of each cube individually, and compare it to the actual value at the end. As a warning, this part of the video includes a lot of equations, so if you're afraid of those, skip to the next scene. In order to do this though, I need to find the values like torque. For you physics nerds, I'll write these down. I'll also need the resistance against the rotation of the rectangle side turning around the core of the cube, which I totally did not just look up on Google because of how blurry this image is. But wait, isn't this just Newton's law for rotation? By moving things around a bit and solving for its angular acceleration, I can actually solve for the angular velocity using this fancy kinematic equation. We know that it turns a certain amount of radians, and we also know that the cube wasn't moving until I pressed the sensor, so that simplifies the equation quite a bit. After solving for the final velocity, and finding the initial and final angles using my tracker, it gives us 351.91 radians per second. That's about 2,990 degrees per second. Makes no sense. That doesn't make any sense. This shows how ideal physics problems and real-world experiments differ. In this case, I calculated for a cube in space with no friction that has the potential to reach an infinite speed given an infinite amount of time and a constant torque. Knowing this now, it's fair to say that physics requires an extensive knowledge on how outside factors can affect the results. I'm going to instead use the servo motor's datasheet to find the exact maximum speed that we can compare the actual speeds to. Using this equation, the angular velocity is equal to the displacement in degrees divided by the displacement in time. This gives us 315.789.
$1 million? Well, definitely wouldn't do what most people do, just like spend it all on, like no stuff.
After a long 10 hours of calculations, 3 hours of script writing, and days of editing, the winners can now be announced. And the winner is Team 2x2 with an average speed of 295.8 degrees per second. At first I thought this project would be very worthless to me, but as it went on, I realized that it helped me to understand rotational dynamics in a very fun and interesting way. Even though Team Shapeshifter lost the least energy due to friction and tension, the teams 2x2 and 3x3 actually caught up really quickly because of their magnets, which gave them an additional acceleration boost. Overall, I think the control team served as a perfect baseline for the experiment as a whole. That's kind of satisfying, actually. That's fine.
can say. And the winner is.
And the winner is
2x2.
And the winner is Team 2x2.
While Team Shapeshifter wasted the least energy from... I'm in the middle of filming. It's fine. You can enter. Okay, even though Team Shapeshifter... Why can't I say it anymore? That's good.
Good enough.
Oh, I should have turned this on.
Brad.
Why are you mewing? Okay, you can sit down now. And you can look into the camera like a pretty princess. It's over there. Okay, Levi, go.